Okay, so in the last lecture we discussed about the central force motion. So, today we will continue with that and some remaining formulation we will complete, and thereafter we will look into the problem of motion of two particles or two bodies under the mutual gravitational attraction. Okay. So, for okay, so now for the gravitational central force motion, whatever the last time we have discussed. So, last time we did not assume anything about the gravitational force, how it is varying, but today we will assume that the gravitational force it varies as the inverse square, okay, of the distance between the two particles, or in this case because the only one particle is present and there is a center of attraction. So, we assume that this gravitational field or the gravitational force due to the center of attraction, it falls off as 1 by r square, or it varies as 1 by r square. So, we have the equation for the motion can be written as F is equal to, where F is indicating the force acting on the particle, is equal to minus g m m by r square u r. In this case, this is the this part it indicates the Newton's gravitational law, where m is the mass of one particle and capital M is the mass of another particle, and the distance between them is r square. Then this is the force acting, and here u under square r, u cap r, this is the unit vector in the direction of r. So, because we are discussing with the central force motion, so here we assume that the only the center of the force is available to us. Okay. So, it may be given in terms of just like writing g times m as mu, okay, and m by r square u r. So, this can be represented as mu by r square m times u r cap. So, where mu is a constant of proportionality, because here we are just assuming it is a central force motion. Okay. So, we may not be aware of actually what is the mass of the center of force of attraction, but here given in this format where this is the proportionality constant. So, we can infer from this that there is some mass involved in that. This is the best way of, this equation is the best way of writing the force of motion in this case. Okay. So, therefore, left hand side we can expand it and we can write it as d square r by dt square, this is equal to minus mu by r square m times u r cap, where u r cap or sometimes it is a u r cap is also written as just r cap to indicate this is a unit vector. Okay. So, here m is the mass of particle in the gravitational field, and u r cap unit vector in the direction of vector r. Okay. R is the distance of the particle from the center of attraction. So, therefore, equation 1 can be written as d square r dt square, this is equal to minus mu by r square u r cap. Okay. Now, let r is equal to r times u r. So, basically r is here the magnitude of the vector r, and u r is the unit vector in the direction of r. Therefore, dy dt r, this becomes so we can differentiate it and write it in this way. Okay. Now, here dr by dt, this is nothing but r dot, which is the component of the velocity vector in the direction of r. So, we can show it here. This is the center of attraction, the particle p is moving here. Okay. So, this is v is equal to nothing but r dot. Okay. And this component then becomes r dot, and this is a vector. So, this is the velocity vector, this is r dot, and perpendicular to this we can break it. Okay. So, this is the radial component, and the similarly the tangential component can be written here, which will be r times theta dot, where theta is the, if suppose we are measuring angle from some reference. So, this is the angle indicated here theta. So, the tangential component can be shown as r times theta dot. Basically, here we are indicating v is equal to r dot is equal to r dot times u r cap plus r times theta dot times u theta cap, where u theta cap the unit vector in theta direction or perpendicular to u r vector. Okay. Therefore, dr by dt, this becomes r dot times u r cap plus r times d by dt u r cap. Now, this is our equation number 2. Issue is to determine this particular value, this particular term. So, this quantity is what will be the how to indicate this quantity, how to remove the differential of the u r cap and indicate in terms of the other known parameters. So, here we have basically u r we can indicate as, suppose this is the u r vector. Okay. So, because this u r vector is indicated in the direction of r. So, after some time delta t, this will rotate by delta theta angle. So, it rotates in time delta t by delta theta angle. So, the new u r then is indicated by So, this u r is at time t. So, another u r at time t plus delta t can be indicated by this vector. So, this is the net change in u r. So, this we can write as delta u r cap. Okay. So, therefore, delta u r cap by delta t, or let us take first the magnitude of delta u r. So, without taking the direction of this. So, this can be approximately written as u r cap magnitude times delta theta, and so divided by delta t, okay. And in the limit delta t tends to 0. So, this delta u r by delta t, then it becomes, okay, this quantity is equal to 1 because this is a unit vector, okay, and this becomes theta dot. So, this quantity basically equals to theta dot. Now, this change, as we are taking this u r here, u r at t. So, as t becomes delta t becomes a smaller and a smaller. So, the change can be indicated by an arrow which is perpendicular to u r vector. So, this is perpendicular to u r vector. So, this vector is nothing but the unit vector in this direction can be indicated by unit vector perpendicular to u r is nothing but u cap theta. Okay. This implies that limit delta t tends to 0, delta u r by delta t cap, this can be indicated by d r by d t is equal to nothing but theta dot times u theta cap. Okay. Therefore, in equation 2, so inserting or inserting equation 3 into leads to dr by dt is equal to r dot times u r cap plus r times theta dot times u theta cap. Okay. Then next step is to find the second differential of this. So, now we can determine d square r by dt square. So, again differentiating this equation number 4. So, this can be expanded okay. So, as usual d u r by dt here it can be replaced by r times theta dot times u theta cap plus r dot theta dot times u theta cap, then r times theta double dot times u r cap, and r times theta dot times du theta cap by dt. Now, this is the term that we have to evaluate. So, as usual we have done, now we can indicate a vector, unit vector by u theta. So, in time delta t, this u vector will undergo a change of u theta t plus delta t. The net change is here delta u cap theta. And this vector rotates by an amount delta theta. See, the vectors are like this. This is the u r vector and perpendicular to this is the u theta vector. Okay. So, both of them they rotate at the same rate. Okay. So, here from this one we can write again that du theta cap by dt, or we can remove the cap sign here and just we can have a look of this, that limit delta t tends to 0. So, this is delta u theta divided by delta t, and delta u theta, how much this is going to be. So, delta u theta we can write from this place, u theta cap magnitude times delta theta divided by delta t. So, this becomes theta dot, and we can see from this place that if we have any change in this vector u theta. So, here delta u theta will be indicated, delta u theta. So, this is your vector u theta cap t plus delta t. Okay. This is vector u cap theta t plus delta t. So, this is the change which has been indicated here in this figure. So, as the time delta t becomes very small. So, the change delta u theta cap, this will be just opposite to the vector u r cap. So, we can write here du theta cap by dt, this is equal to theta dot times u r cap with a negative sign, because this is indicated in this negative direction of u r, just opposite direction of u r. So, I will make a better figure here. This is u r, this is u theta, this is u theta cap t plus delta t, okay. And this is the change here delta u theta. Okay. So, this delta u theta, as delta theta becomes very small or delta t becomes very small, this is delta theta. So, this vector just becomes opposite to the u r vector. So, we have written with a minus sign here in this place. So, in general we can write u theta is equal to minus omega cross u theta cap. Okay. So, omega is nothing but here theta dot, okay, and a corresponding vector which will be perpendicular to both theta and u r. So, this will give us theta dot times u r cap. Okay. This can be easily seen from here. So, now completing we can write d square r by dt square is equal to r double dot u r cap plus 2 r dot theta dot u theta cap plus r times theta double dot minus r times theta dot square times u r cap. Okay. Now, collecting similar terms together, this gives us u r cap, and here we have missed out u theta. So, we can insert here u theta cap. So, this becomes 2 r dot times theta dot plus r times theta double dot u theta cap. Okay. This is our equation number 5. Okay. So, from equation number 2, from equation number 2 and 5, we can write r double dot minus r theta dot square u r cap plus 2 r dot theta dot plus r theta double dot u theta cap, this is equal to minus mu by r square u r cap. Now, comparing the coefficients of the unit vector u r and theta on both sides in this equation number 6. Comparing the coefficients of u r and u theta on both sides, we have r double dot minus r theta dot, and this is here one correction is there. R theta, here the square is not outside, this is inside. So, here a square is inside. Okay. So, comparing these coefficients, so this gives us r double dot minus r times theta dot square, this is equal to minus mu by r square and 2 r dot theta dot plus r theta double dot, this is equal to 0 because there is no term of u cap theta on the right hand side in equation number 6. Okay. So, this is our equation number 7 and this is equation number 8. So, now after this simplification, we can further explore this equation. Okay. So, let us take this equation 2 r dot theta dot plus r times theta double dot equal to 0. If we can represent it in a better way, so we can get more information or we can understand this system in a much better way. So, if we write r times theta dot square, if we differentiate this quantity, suppose, so what we get here r dot okay, r dot times theta dot square plus let us take the quantity dy dt r square theta dot, not r times theta dot square. So, if we differentiate this, so this quantity then it will become 2 times r times r dot plus r square times theta dot, theta double dot. Okay. So, now we can see that this quantity and sorry, and here the quantity theta dot is missing. So, we put here theta dot also. So, this quantity and this quantity they differ by one term which is r. So, we can take r outside. So, this becomes 2 times r dot theta dot plus r times theta double dot. Okay. So, because r is not 0, so we can easily write d by dt r square theta dot. Okay. This quantity is equal to this quantity equal to 0. Okay. Here r is not 0. So, if we integrate it, so r dot r square times theta dot, this becomes equal to h equal to a constant. Okay. So, what this quantity is? This quantity is nothing but the angular momentum vector per unit mass. Okay. We can check it from here. This is the r vector, this is the center of attraction. Particle is moving along this path. So, this is the velocity vector. Okay. This is the r dot component, and this component perpendicular to this is r times theta dot. Okay. So, the angular momentum this will be given by r times angular momentum r times theta dot. Okay. This we are writing in scalar notation. If we want to write the same thing in vector notation, then we have to write here r cross v. So, this is the angular momentum vector h here. Okay. And if we expand it, we get the same quantity. So, here this is simple multiplication, while here this is the cross product, and we can check from this place h is equal to r cross. Now, v becomes r dot times u r cap plus r times theta dot times u theta cap. Okay. So, unit vector in the direction of r is nothing but u r. So, this cross product will vanish, leaving us with r cross r times theta dot u theta cap. Okay. So, the angular momentum vector this will be perpendicular to both the r vector and the u theta vector. Okay. And magnitude of this angular momentum vector h can be written as r square times theta dot, because the magnitude of r vector will be r. So, this term makes it r square and times theta dot, and the unit cross product of unit vector will give a unit vector. You can easily write here h is equal to h magnitude is equal to r square theta dot. So, this is the information we get from the quantity which is indicated here. Now, after getting this information, we can take the equation number 7. Now, we can tackle equation 7. So, we have from equation 7 r double dot minus r times theta dot square, this is equal to minus mu by r square, okay. And here we can name this as equation number 9. So, theta dot will be equal to h by r square, and this we get from equation number 9. Okay. So, insert this into this equation. Okay. So, this gives you r double dot times r times theta dot. So, insert it. So, this will become r square whole h by r square whole square is equal to mu by r square. Okay. R cube. Now, this equation is, you can see it is a in this usual way we cannot tackle it, we cannot solve it, but if we do some manipulation it will become easier to solve it. Okay. So, this we write as the equation number 10. Now, let us put 1 by r is equal to u. Okay. Therefore, 1 by r square with a minus sign dr by d theta okay, or we will do like this. What we want, we will look for this quantity r double dot. Okay. So, if we differentiate with first with respect to t, okay, 1 by r. So, this will be du by dt. What we intend to do here, we want to replace the variable independent variable t by theta. So, we will be using independent variable theta instead of t, and then this equation will get simplified, and then we will be able to solve it. Okay. So, for doing this, this is t. We can write it in this way. Okay. So, the quantity now this will become okay, by r square. Okay. So, what we will do here, we are looking for dr by dt. So, okay. Let us write 1 by r is equal to 1 by u we have taken. So, we will better express it as r is equal to 1 by u, then it will be easier to work it out. Okay. So, therefore, we can write dr by dt, this is equal to d by dt 1 by u, and so this way it is easier to write. So, therefore, this quantity here becomes du by d theta and minus 1 by u square times d theta by dt is nothing but theta dot, and on the left hand side we have r dot. Okay. But we need r double dot, therefore, we need to differentiate this once more. So, u theta du by d theta will write as u prime. U prime is nothing but du by d theta. So, next time once we differentiate this further, so this becomes r double dot equal to minus d by dt 1 by u square u prime theta dot. Now, we need one further substitution for theta dot here, because we are not going to put here theta double dot, we want to replace this. So, we will do it further here in terms of 1 by u square u prime, and theta dot we know that r square theta dot is equal to h. Therefore, theta dot we can replace by h by r square, and this is nothing but h times u square. Okay. So, theta dot then becomes h times u square. So, the whole thing then looks like u prime h, where h is a constant. So, therefore, r double dot this becomes minus d by d theta times u prime h times d theta by dt. Again we need to replace this d theta by dt in terms of h and u. Okay. So, now this becomes d square u by d theta square times h times theta dot. Now, theta dot is h by r square is equal to nothing but h times u square. Okay. So, the whole thing then turns out to be minus h square u square d square u by d theta square. So, if we go back to our equation number 10, this is our equation number 10. Okay. So, now in equation number 10, we have r double dot, we can insert from here minus h square u square d square u by d theta square, and minus h square by r cube. So, 1 by r is nothing but u. So, we can simply replace this as u cube equal to minus mu times u square. 1 by r square becomes u square. Okay. Cancelling the minus sign on both sides. So, this can be simplified as d square u by d theta square plus h square u cube by h square u square is equal to mu square by h square u square. Okay. So, ultimately what we are going to get, cancelling it out, this is mu, this is u square cancels out, mu by h, mu by h square. This is our equation number Okay. So, now this equation we can look into the equation number 11. This is a linear second order differential equation, and right hand side is mu is a constant and h is a constant, because this is the magnitude of the angular momentum vector. Okay. Therefore, it is easier to solve it, and the standard solution to this equation is available. So, solving equation 11. Okay. So, the total solution u will consist of the particular integral and plus the complementary integral or complementary part and the particular integral. So, the complementary part, this can be written as C 1 times cos theta minus beta, and the particular integral, it is very easy to see in the equation number 11. If we put u is equal to mu by h square. So, because this term is a constant, so this will become automatically, this term will become 0, and both side will then become equal. Therefore, particular integral mu by h square, u is equal to mu by h square, it satisfies this equation. So, particular integral we can write as mu by h square, and thereafter we can put u is equal to back to 1 by r. So, this becomes C 1 cos theta minus beta plus mu by h square. So, this gives us the solution to our second order differential equation, which is equation number 11. Okay. We can further simplify it and put in a standard format. So, which this format is known as the equation of the conic section. Okay. So, let us modify this little bit. Okay. What we can do, we will write here as h square by mu. We bring the whole thing from this side to this side. So, this will become h square by mu divided by r, and this term will become C 1 times h square by mu cos theta minus beta plus 1. Now, putting h square by mu is equal to L, okay, and this quantity is known as semi lattice rectum. Okay. And we put C 1 times h square by mu is equal to E. This term is called eccentricity. Okay. So, this equation then gets reduced to L by r is equal to 1 plus E, and also put theta minus beta is equal to phi. So, this becomes so this is the equation of a standard conic section. Okay. So, here two parameters are three parameters in fact are involved. One is the two parameters are there, L and E is the eccentricity and L is the semi major axis, and we have the two variables involved here, which are the radius vector and this is the phi, which is called the true anomaly. Okay. So, we will look into this pictorially later on. We will leave with this at this stage. Okay. So, here we can write this as further L by 1 plus E cos theta is equal to r. So, this is the radius described in terms of theta. Now, if E is equal to 1, this conic section becomes a parabola. If E is greater than 1, then the conic section is hyperbola. If E is less than 1, but greater than 0, then this conic section is an ellipse. Okay. If E equal to 0, so this conic section gets reduced to a circle. Besides, other cases are there, we will consider it later on. So, we stop at with this solution at this point. So, our working with the central force field motion, it is a complete right now. So, now we are going to get into the two particle motion, means there are two particles and they are moving under the mutual gravitational attraction of each other, and then we try to look into whether this problem is solvable or not, or if solvable, then what are the assumptions involved for solving this problem. So, here the problem was very plain, that we have a center of attraction and then we want to describe the motion of a particle. So, using very simple mathematics, we have been able to describe the motion of the particle in the central force field as a conic section. Now, depending on the value of the eccentricity here, this turns out to be either an ellipse or a circle or a hyperbola or a parabola. So, these are very relevant in the case of a satellite, okay, because if we consider from the point of view of a satellite. So, once we inject the satellite into the orbit, so at the time of insertion or at the time of injection into the orbit, what is the value of the velocity, or means in which direction the velocity vector is there, what is its magnitude. So, that will decide what kind of orbit this is going to be. Okay. So, accordingly the E will be fixed. So, the velocity vector and the radius vector together with both of them are having 3 components, total of 6 components. So, initially we know these 6 components, they are known to us from the onboard measurement units are there, this inertial measurement units are there. So, from there we have the velocity components, 3 components of velocity and 3 components of the radius vector, they are available. So, they help in determining all these parameters which are involved here. Okay. So, let us look into the case of an ellipse. So, once E is greater than 0, but less than 1. So, this is the case of an ellipse. So, how does this conic section look like, and how this can manifest in the form of an orbit. So, let us consider that we have the inertial axis here x, y and z. So, any satellite, what we are showing here, this is the inertial axis x, y and z. Inertial axis means its orientation remains same and it is a non-accelerating reference frame. In fact, non-accelerating reference frame, it is a physically nowadays it is a fixed in the ICRS system. This is called the International Celestial Reference System, but once we work with the because we do all the measurements from the earth. So, we fix an axe parallel to that and fix at the center of the earth, but it is a non rotating, means its orientation remains parallel to the GCRS, and this the orientation of this reference frame, it will remain parallel to the ICRS. So, this is parallel to ICRS, and this we will term this whole thing as the geocentric celestial reference frame or the reference system. So, in the GCRS, so x, y, z here, this indicates and the reference frame GCRS. So, in fact, this GCRS will have, because suppose we have the earth here. So, at the center of the earth we are fixing this inertial reference frame GCRS. So, and this earth will be going around the orbit around the sun, and the satellite is moving around the earth. So, orientation of this reference frame while the earth goes around the sun, it remains same, it does not change, means it is a snapshot at this instant and another snapshot at another instant, they will look exactly parallel to each other, but because it is going in a elliptical orbit. So, it has certain amount of acceleration. So, in true sense this is not exactly an inertial reference frame, but for our earth purpose or for many of the our measurement purpose, this will serve as the inertial reference frame, because this acceleration is quite small. And therefore, if we look into this case, so here we have the say earth available, and on the earth we have, this is the equator of the earth. So, this is the equator, and here somewhere say our ground station is there. So, from the ground station we are looking at some satellite in the sky here. So, the same satellite is suppose indicated here by S, and the orbit of the satellite around the earth may look like So, this orbit is indicated here by this particular curve, and we can extend it below. So, the solid line is above the x y plane, and the dotted line lies below the x y plane. Now, in this plane the satellite is lying here, and this is the radius vector of the satellite. This angle from here to here, this is capital omega, this is called nodal angle. The line n n prime, this is known as the line of nodes. So, satellite position is measured from certain position which is called perigee. So, say this is the perigee of the satellite, this is the nearest position of the satellite from the center of the attraction, or in this case from the center of the earth. So, the angle from here to here, this angle is written as small omega, and this small omega, this is nothing but argument of perigee, and the angle from here to here up to the satellite, this is written as theta, and theta, this is called the true anomaly. So, in this equation that we have referred, this theta is nothing but the true anomaly. So, here we have the theta true anomaly. Besides, so we have covered here capital omega small omega and theta, these are the 3 parameters. Beside this, to determine or to describe an orbit, we have another 3 parameters. So, total of 6 parameters. So, we will describe this in the next lecture, and then we will continue with the motion of 2 particle system, and we will further develop that into the 3 particle system. Okay. So, thank you.